Hello everyone, I hope you all are well. I am Priyanto Kumar Choudhury. Today I will discuss about Aho-Chorasick algorithm. Basically, it is a string searching algorithm. It was invented by Alfred V. Aho in 1975. It is a kind of dictionary matching algorithm that locates element of finite set of string within an input text. So these are the three steps of Aho-Chorasick algorithm. First step is tree. Basically, it is known as digital tree or prefix tree. The second step is suffix tree. It is also known as failure links. And last and final step is output links. In this slide, we know how to build a tree. As we see in the right side, we have 4 strings. So we build a tree through those 4 strings. Now we will work on the first string, which is A, C, C. Here R is the root node and also R is our current node. So R will search, does it have any child? No, because R is our root node and it has not any child. So we make A state. Now A is our current node and also A is child of R. So as R is our current node, we came here. Now R will search, does it have any child? No. So we make another state which is C. Now C is our current node. Also child of R. R will search, does it have any child? No. So we will make a state which is also C. We came node C to node C. It is our final state and also child of C. By coming to the final state, my first string is done. Here it is A, C, C. Move on the next string A, T, C. Here root and current node is R. R will search, do I have a state named A? Yes, there it is. And A will search, do I have a state named T? No. So we make a state named T. We came T and T is our current node and also child of A. T will search, do I have a state named C? No. So we make a state which is C and this is our final node. By coming to the final node, our second string ATC is done. Now we move to the third string which is CAT. R will search, do I have a state named C? No. We make a C. So it becomes our current node and also child of R. C will search, do I have a state named A? No. We will make a state named A. And A is our current node and also child of C. Now again A will search, do I have a state named T? No. So we make a state named T. By coming the final node, my third string which is CAT is done. Now we will work on the fourth string which is GCG. R will search, do I have any state named G? No. We make a state named G. And G will search, do I have a state named C? No. As G is our current node, G has no child, so we make a state C. And C will search, do I have any state named G? No, C has no child, so we make a state named G. By making G, our tree is done. This is our tree which I did it in previous slide, and this is our dictionary. What will we do? we will do, can this tree find this dictionary element? So the first dictionary element is G. Root will search, is there any G? Yes, root can find G. And G will search dictionary second element, which is C, and also G will find C. And C will search the dictionary third element, which is A. But the interesting thing is this C cannot find A, because our second step is G and this is our final step. So this tree only work on successful link, not failure link. So we will make failure link in the next slide. Before I go to the failure link, we should learn what is the proper suffix tree. Let's take an example, man. Here the suffix link would be last two element of man, which is an. What is the suffix link of an? Is just n. And what will be the suffix link of n? It will nothing but an empty string. And the next slide we will build a failure link. We will make failure link on the previous tree. Here root is one single string, which is r. It will connect it to itself. And also there are three child of r, which are a, c, g. As they are single strings, so they will also connected to the r. Now a is the parent of c and t, but we will work on the c first. C will search, is there any C state which is connected to the root? Yes. C will connect it to the C like this way. Now we will work on the final state C. C will also search, is there any C state which is connected to the root? Yes. So C will connect it to the C like this way. So our first string of suffix link is done. Move on to the second string, which is A, T, C. Here A is already connected to the root. Move on to the T. T will search, is there any T which is connected to the root? No, there. So T will also connect it to the root directly. Now move on to the C. C will work as same as before. My second string is also done. Move on to the third string, which is C, A, T. C is already connected to the root. Move on to the A. A will search, is there any A which is connected to the root? Yes. A will connect it to the A. Move on to the T. Here comes the interesting part, because there is no T which is connected to the root, but T is partially connected to the root through A. So T will connect it to the other T. Move on to the last string, which is G, C, G. Here G is already connected to the root and C will also work same as before. And the last element of G will search, is there any G state which is connected to the root? Here. So G will connect it to the G like this way. So our failure link is done. Now we will discuss about the output links. As we see, this tree only work on the successful link, but after making the failure link, this tree will also work on the unsuccessful link. So basically we have a dictionary which is C, A, T, C, G. Can this tree find this dictionary's element? So root will search, is there any G? Yes. Root will search G. G will search, is there any C? Yes. G can find C. And C will search, is there any A? So basically we cannot find A after C, but when I set up a failure link, this will happen. So C will connect it to the DC, and DC is called output links. So now this C can find A. Now move on to the next step. A will find, where is my T? So the next step is finding T. So here is my T. T will search, is there any C? So this T is our output links, and this T will also find C. So this T is connected to this T, and this T can find C. And the last and final step is where is G, and C can also find G. So this is my output links, and this C will connect it to the C, and this C will also connect it to the C, and this C can find G. This is the mainly output links. So we can find any dictionary word to making failure links. Now we will talk about pseudocode and time complexity. In the Aho-Chorasick algorithm, first of all we to hook the every string, then we split those string, then the two counter I and state, and we will define the every parent is a current node, and the key should be the upper cases. Then take the while loop where I goes to the k. Here k is the length of the words. Then take the if and else statement. This if and else statement basically check the if my current node is parent or not. If the current node is parent, then child equal to parent. In the else statement, the new state will the updated and so on. And the time complexity of the Aho-Chorasick algorithm is big of n plus m plus z. Here n is the length of a string, m is the number of characters, and z should be the number of occurrence. Advantages: it is a very good and advanced algorithm, so it provides a solution to many real life problems. For example, installation detection, plagiarism detection, digital forensic, etc. It is one of the fruitful algorithm in the computer science. That's it. I hope I was able to explain to you about the Aho-Chorasick algorithm, and thank you.